All right, now let's put Lagrange's theorem to work. Just remember what Lagrange's theorem is, that if you have H is a subgroup of G, and you have then the order of G divided by the order of H is equal to the number of cosets. So in particular, it's an integer, which means that the order of G evenly divides the order of H evenly divides the order of G. Right now, let's think about a special case of this. We could take, for example, we could take H to be the cyclic subgroup generated by any element in big G. So I could take H as this. Then the order of H is what we called the order of G, little g. All right. So what does this tell me? If the order of H divides big G, that means the order of any element in the group must divide the number of elements in the group. Okay? That's what this proposition says. The order of any element little g in the group big G divides the number of elements in big G. All right. And this proof is basically what I set up here. You can read it yourself. Now we can apply this, and let's apply it to the multiplicative groups of modular multiplication. Now remember that U of n is the multiplicative group of numbers less than n that are relatively prime to n. And there is a special notation for this quantity. Phi of n is the number of natural numbers that are less than n and relatively prime to n. Okay. So alternatively, we can say phi of n is the number of natural numbers m, where m is less than n, and the GCD is equal to 1. Okay. So we also define phi of 1 is equal to 1. So this is called the Euler-Phi function. And for instance, phi of 2 also equals 1 because there's only one number less than 2, which is relatively prime to 2. Phi of 3 is 2 because there's two numbers 1 and 2 which are relatively prime to 2. So phi of 3 is 2. Phi of 4, well, how many numbers less than 4 are relatively prime to 4? Well, there's 1 and 3, so phi of 4 is 2. Sorry, it should be 2. Phi of 5, well, phi of 5 is 4 because 1, 2, 3, and 4 are all relatively prime to 5. Okay. All right, so here's some exercises where you will compute some other phis. And let's now apply Lagrange's theorem. All right. Now, U of n, the order of U of n is equal to phi of n. Okay. All right. Now, so let's take any element in U of n. Let's say A is in U of n. That means that the order of A must divide phi of n. Okay. Now what does that tell me about A to the phi of n? Well, phi of n is equal to the order of A times some number. So that's equal to A to the order of A times k, where k is some integer. All right, but that's the same thing as A to the order of A to the kth power. Now what's A to the order of A? A to the order of A is the identity, always equal to the identity. So this result is identity to the k, which is equal to the identity. All right, now the identity in our case is 1 because we're looking mod n. So in fact, what we have here is this result. Let n integers be such that the GCD of A and n is equal to 1, then A to the phi of n is congruent to 1 mod n. Now, this proof here, I did A is in Actually, I shouldn't have put absolute values there. It's just A is not in absolute U of n, A is in U of n. So if I take any number less than n that's relatively prime to n, this will be true. And then because this is a modular statement, then it's true for any number that's modular equivalent to A. Okay, so I was a little more careful with the proof in here, but the idea is similar, that you take any element, raise it to phi of n, that gives you the identity, and phi of n is divisible by the order of A, so that gives you that you actually get the identity here. All right, so a very nice theorem that says some amazing things about raising numbers to powers and taking the result mod n. You can imagine if n is large, how long it would take you to compute this. And computing phi of n is not that easy, but we get this result automatically from theoretical reasons. All right, now there's a special case where the n is prime. Now if n is prime, then what is phi of n? So let's consider phi of p. Well, phi of p is just equal to p minus 1. Because all the numbers less than p are relatively prime to p. All right. So that gives us this result that a to the p minus 1 is congruent to 1 mod p for no matter what a that is relatively prime to p. Of course, if a is divisible by p, then a to the p minus 1 will be congruent to 0 because a is divisible by p. Now we can go even farther than this. Here we're talking about the multiplicative group of numbers mod p. In fact, any group with order p can have the same argument applied. So we get this proposition here. If G is a group with prime order, then G is cyclic, and any element is a generator. Why does this follow? Because we know that G to the p is equal to G. So that means that the order of G is going to be equal to P. If the order of G is equal to P, then the entire group will be generated by G. Okay, so if I have a group of prime order, no matter what element I take besides the identity, the order of that element is going to be equal to P, which is the order of the group. So that tells me that the orbit or group generated by G must be equal to all of G. And that means that G is cyclic and that any group is a generator. Okay, let's stop there.